We have one more matter that we must discuss before we start linear algebra. This is in part because the subject is critical to linear algebra, but also because the subject is critical to all of abstract algebra. And as you know, this lecture series is the first of multiple lecture series covering abstract algebra. And this is the subject of partially ordered sets and their special cases, their relatives called lattices. This subject is critical to most of mathematics, perhaps all of mathematics in one way or another. The subject of order is essential in mathematics. But like the subject of transfinite cardinal numbers developed by Cantor, this area of mathematics received some immediate bad press. Unlike the subject of transfinite cardinal numbers, where by the early 1900s people began to see how important it was, the reputation of lattice theory and theory of partially ordered sets has persisted for some reason. I myself have felt this prejudice. I wrote a graduate level textbook on order and lattice theory, and I wanted it to be published in the Springer Graduate Texts in Mathematics series, where I had previously published 3 books: Advanced Linear Algebra, Field Theory, and Coding and Information Theory. But the book was rejected to be included in the series because the reason it was given was that this theory is not mainstream mathematics. So that is a shame, and it shows that the prejudice related to this subject has continued into the present day. I'm going to read you an excerpt from an article that my friend Giancarlo Rota wrote for the notices of the American Mathematical Society. This is, let me see if I have a date on here, December 1997. Okay. Giancarlo and I, as you may know, Giancarlo Rota was a very famous combinatorialist. He was a professor at MIT and also not only a professor of mathematics but a professor of philosophy. And when I joined the faculty at MIT in the mid-70s, 1970s, we became good friends. We wrote a paper together on the umbral calculus, and we spent a lot of time together. So he and I were good friends until his death. In any case, I'm going to read you a little bit of this article because I think it's interesting. Never in the history of mathematics has a mathematical theory been the object of such vociferous vituperation as lattice theory. Dedekind, Janssen, Courage, Malchev, Ore, von Neumann, Tarski, and most prominently Garrett Birkhoff have contributed a new vision of mathematics, a vision that has been cursed by a conjunction of misunderstandings, resentment, and raw prejudice. Giancarlo had quite a way with words, and he didn't pull his punches, at least not in this case. The hostility towards lattice theory began when Dedekind published the 2 fundamental papers that brought the theory to life well over 100 years ago. Kronecker, and you might remember I mentioned Leopold Kronecker and his disapproval of Cantor's theory. He called Cantor a charlatan, a scientific charlatan, and a corrupter of youth. He was a very busy man, trashing other mathematicians for some reason. Kronecker, in one of his letters, accused Dedekind of losing his mind in abstractions, or something to that effect. I took a course in lattice theory from Oystein Ore while a graduate student at Yale in the fall of 1954. The lectures were scheduled at 8 a.m., and only one other student attended besides me. It is the only course I've ever attended that met at 8 o'clock in the morning. The first lecture was somewhat of a letdown, beginning with the words, "I think lattice theory is played out." Ora's words have remained imprinted in my mind. For some years, I did not come back to lattice theory. In 1963, when I taught my first course in combinatorics, I was amazed to find that lattice theory fit combinatorics like a shoe. The temptation is strong to spend the next 50 minutes on the mutual stimulation of lattice theory and combinatorics of the last 35 years. I will, however, deal with other aspects of lattice theory, those that were dear to Garrett Birkhoff and which bring together ideas from different areas of mathematics. So, there you have it. And now let's begin. The place to start, I guess, is with the definition of a partially ordered set. A partial order, as P is a non-empty set, a partial order on P is a binary relation, which I will denote by this funny-looking less than or equal to sign, the equal sign, where the top symbol is kind of curved, that has the properties listed below. For A and B in P, this expression is read A is less than or equal to B, or B is greater than or equal to A. And I'll stop right here. This is only language, and you should not infer from this language that less than or equal to or greater than or equal to has anything to do with numbers. It might, but it might not, as we'll see when we do examples of partially ordered sets. So here are the properties. The binary relation must be reflexive, A less than or equal to A for all elements in the set. Anti-symmetric, A less than or equal to B and B less than or equal to A implies A equals B. And transitive, A less than or equal to B, B less than or equal to C implies A is less than or equal to C. I should mention, by the way, and I guess I didn't, that we're coming to it. Good. The pair P and the binary relation is called a partially ordered set, which is abbreviated oftentimes Postset. I guess because people are somewhat lazy. Sometimes the ordinary less than or equal to symbol or ordinary less than or equal to symbol is used in place of this curly symbol. But since this may be your first careful exposure to this concept of Postset, I didn't want to use this symbol because it might be misleading. It might refer to the usual less than or equal to, say, on the real numbers. So I use the more generic symbol. The set P is called the underlying set of the postset. Two elements, x and y in P, are comparable if either x is less than or equal to y, or y is less than or equal to x. Otherwise, x and y are incomparable or parallel, and that's denoted with this parallel symbol. This is a good place to interject. Partially ordered sets, the word partial means that it's not required that every two elements be comparable. A postset is called a totally ordered set or linearly ordered set if every pair of elements is comparable. You are probably more familiar with order in the context of total order rather than partial order. And so you'll find some surprises that certain things can happen, that certain concepts exist in partially ordered sets that are not totally ordered. If x is less than or equal to y, but x is not equal to y, then we write x less, this would be read x is strictly less than y. Some examples. We have the usual order on the natural numbers, also on the integers, also on the real numbers. These are total orders, so they're not very representative of partially ordered sets. Here are the most famous, arguably, the most famous partially ordered sets that are not totally ordered. The power set of any set S, which, as you know, is the collection of all subsets of S, is ordered by set inclusion, because that's reflexive, antisymmetric, and transitive. Incidentally, I probably should have said earlier, as you know, an equivalence relation is a binary relation that's reflexive, symmetric, and transitive. So the only difference between an equivalence relation and a partial order is the symmetry. Instead of being symmetric, partial orders are antisymmetric. That makes a world of difference. The two theories are not related. Equivalence relations are totally different than partial orders. In the power set, ordered by set inclusion, as long as there's at least two elements in the set, then this is a partial order but not a total order. So if we take two elements A and B in the set S and form the singleton subsets, neither one of these is contained in the other, because A and B are different. So the order is not total. These are not comparable, these two singleton subsets. One other definition I forgot to read this last line here. A non-empty, totally ordered subset of a postset is called a chain. You could just call it a totally ordered subset, but I guess, again, because people like conciseness, it is called a chain in the postset. So here's an example of chains. Let's say S is the set of numbers from 1 to 6. Then this family of 4 sets These are subsets of S, so they belong to the power set of S. This is a subfamily of P of X. Oops. P of S. This is a chain because given any two members of this family, one is contained in the other. It's straightforward just to check that. But this family is not a chain, because if you look at the last two members of the family, these two sets, neither one is contained in the other, so these are not comparable. So the order here, set inclusion, is not total. Another important partial order that's not total order is divisibility on the natural numbers. Divisibility is reflexive, antisymmetric, and transitive, but for example, 2 does not divide 3 and 3 does not divide 2, and so this Postset, the natural numbers under divisibility, is partially ordered but not totally ordered. In fact, no two primes are comparable. Neither one divides the other. Incidentally, the natural numbers has two very important and very common partial orders on it: the usual order and divisibility. So this is an example that illustrates that the underlying set alone is not a partially ordered set. You must specify the order, and oftentimes there is more than one possible order on a set that turns out to be important. Here's a final example for now. Let X be a non-empty set. A partial function f on X is a function whose domain is a subset of X and whose range is, or codomain is X. So f maps a subset of X to X. If f and g are partial functions on X, we say g is an extension of f if the domain of G contains the domain of F. So to get the domain of G, we enlarge the domain of F. And that F and G agree on the smaller domain, the domain of F. This idea is something you would have seen if you took my transition course, but you might also have seen in calculus. I'm not sure. I haven't taught calculus for 40 years, and I'm very happy about that. If we let P be the collection of partial functions on X, we can order P by extension, f less than or equal to g if g is an extension of f. This is reflexive, antisymmetric, and transitive. It's a partial order. So the family of partial functions is partially ordered by extension. It's convenient to introduce extension, if you'll forgive me, of the use of the order symbol by applying it to subsets of a postset. So if S and T are subsets of the postset P, then when we write this, the subset S less than or equal to the subset T, what we're saying is that every little s in big S is less than or equal to every little t in big T. So it's just a shorthand notation to describe this situation. Everything in S is less than or equal to everything in T. And if T is just a singleton set little t, then we can drop the curly braces and just write it this way. So this means that everything in S is less than or equal to the element t. And this means everything in S is bigger than or equal to the element t. So if I write this, it looks funny, but it's simply shorthand notation for 2 divides 20, 4 divides 20, 5 divides 20, and 10 divides 20. The notions of upper bound and lower bound occur quite frequently. And using this very convenient notation I just described, we can give concise definitions. So let P be this ordered pair. I'm just going to say let P be a partially ordered set. There's a generic less than or equal to here. And let S be a subset of P. An upper bound for the subset is an element in P that is bigger than or equal to everything in S. That's an upper bound for S. Note that an upper bound is not required to be in the subset. It's only required to be in the postset, obviously. Okay? If you want to discuss upper bounds that are in the subset, you have to explicitly say this upper bound is in the subset. The dual concept is lower bound. So a lower bound for the subset S is an element that's less than or equal to everything in the subset. Here's an example in the postset P of X, where X is the set containing 1 through 6. This subset, empty set, set containing 1, 2, set containing 2, 3, has several upper bounds. The smallest upper bound is going to be the subset of X that contains these 3 subsets. Well, that would be the union. And the union of these 3 is the set 1, 2, 3. So this is an upper bound for the family S. And in fact, any upper bound for this family is going to have to contain the union. So that's why the union is the smallest upper bound. And in fact, if you do a little bit of counting, you will see that there are 8 different upper bounds for this subset. Sometimes we can describe a finite postset, and even in some infinite postsets, we'll see an example of that later, using a diagram called a Hasse diagram. It shows the elements of the postset. So in this case, these are the elements. This is the underlying set for the postset. And the order is divisibility. So the Hasse diagram has a dot labeled with each element of the underlying set, and it has lines connecting pairs of dots. And the way this is read is if the elements X and Y of the postset are connected by a path that goes up at every step from X to Y, then that tells us that X is less than or equal to Y. So for example, here's 2. There's a path going to 4. That path always goes up, so 2 divides 4. There's a path from 2 to 8, always going up, so 2 divides 8, 2 divides 72. We can get from 2 to 9 by a path, but it doesn't always go up. That one leg of the path goes down, and 2 does not divide 9. So it's all here in this picture. The entire partial order is described by this picture. One of the most important concepts that arises in the theory of partially ordered sets is that of extreme elements. So let's consider the posets. We've got two posets here represented by these Hasse diagrams. Call this underlying set S, call this one T. The order in both cases is divisibility. The poset S under divisibility has a largest or maximum element, 12. Every other element in the set S is strictly less than 12. Or another way to say that is every element in the poset is less than or equal to 12. But the poset T does not have a maximum element. However, it does have what you might call the next best thing. Let me see if I can move this stuff around so you can continue to see the Hasse diagrams while we discuss this. That's going to be a little bit difficult. Maybe the best thing to do here is just to redraw one, two, three, 4, and 9. Okay. So what's going on in this poset? Well, there's no maximum element, but there is an element, say call it little m, that has the property that no other element is larger. It's not quite the same thing as saying everything else is smaller. This is saying no element is larger. Now in a totally ordered set, those are the same, but in a partially ordered set, they're not the same. Take the element 4. It is not larger than everything else in the poset. It's not larger than 9, it's not larger than 3. Remember, larger means a multiple of. 4 is not a multiple of 3. In other words, 3 does not divide 4. So 4 is not maximum. Neither is 9. But both of these elements have the property that there's nothing bigger than them in the poset. Or put another way, for the element 4, everything else in the poset is either smaller than 4 or parallel to 4, incomparable. So 2 is smaller, 1 is smaller, 9 and 3 are parallel, incomparable. Same thing for 9. Everything else is either smaller than 9 or incomparable to 9. Elements with that property are called maximal. So the word ends in al rather than um. Here's another example. Let S be the set 1, 2, 3, and consider the poset, which I denoted by P sub 2 of S. This is the family of all subsets of S of size 2 or less. So it's almost the whole power set. The only thing that's missing is the set S itself. Okay, but that's not the point here. This poset has no maximum member. There's no subset in this family that contains all of the others. but it has 3 maximal elements. The doubleton subsets are maximal. Nothing is bigger than any of these 3 subsets. And if you want to draw the Hasse diagram, that might help illuminate this example. Here are the formal definitions. We have a partially ordered set, a maximum, also called the largest or greatest or biggest element. In P is an element, little m in P, that is greater than every other element, or in other words, greater than or equal to all elements. And that can be written this way. So you could also say it's an upper bound for everything in the postset. On the other hand, a maximal element is an element, little m, with the property that no other element is larger than m. So if little p is in P, little p is not greater than m. Or you could say it this way. If little p is in P, then either little p is less than or equal to m or parallel to m. The dual concepts are minimum and minimal. And so they look very similar to the maximum, maximal definitions. What's the relationship between maximal and maximum? Didn't do this right here. I have to fix this. Well, if a postset has a maximum element, and it doesn't have to, for example, the natural numbers under the usual order, there's no greatest natural number. But if a postset has a maximum element, it will be maximal, and it will be the only maximal element. And that is something you should try to prove if you want to get a real handle on this. On the other hand, if P has no maximum element, it might not have any maximal elements. It might have 10, 20, 50, any number of maximal elements. It might have infinitely many maximal elements. And I would urge you to find examples. You can draw some Hasse diagrams that demonstrate that all these are possible. No maximal, any finite number of maximal elements, infinitely many maximal elements. In a totally ordered set, a maximal element, if it exists, will be maximum. And so in the context of totally ordered sets, which is what most people are used to until they study partially ordered sets, the concept of maximal and minimal is not really important because it's equivalent to maximum and minimum. So this may account for the fact that if you haven't studied postsets before, you haven't seen the concepts of maximal and minimal. But they are critically important. Well, this discussion raises the question, if you have a postset, how do you tell whether it has a maximal element or not? That's a very interesting question. And unfortunately, I can't really devote the time it would take to go into details. But what I will do is show you a theorem that concerning the existence of maximal elements that we will use several times in the text. It is called Zorn's lemma. If P is a partially ordered set in which every chain has an upper bound, then P has a maximal element. So this is really the reason, or one of the important reasons, that we are going through this discussion, that we talked about chains, that we talked about upper bounds, so that we could understand Zorn's lemma. We will need Zorn's lemma, for example, to prove that every non-trivial vector space has a basis. Okay? That may mean something to you now, or may not if you've not studied vector spaces at all. Some freshman, sophomore level linear algebra courses, in my experience, at least mention vector spaces in general, and some don't. So, Zorn's lemma, as you may know, is actually one of the many statements in mathematics that are equivalent to the famous axiom of choice. And I don't really want to digress here and go into any more details. If you looked at the transition lecture series that I did, there is more detail on this. Okay, so let me get these pages separated here. I hate this when they stick together like this. Okay, there we go. Among all upper bounds for a subset of a postset, if there are any, the most important upper bound is the smallest one, the least upper bound. Assuming it exists, it may not exist. Okay. Here's the definition. We have a postset and a subset S of P. An upper bound A for the subset S is a least upper bound if it is simply the smallest of the upper bounds. And so we can write that in symbols. This tells us that A is an upper bound for S, and this conditional statement tells us that if B is also an upper bound for S, then B is bigger than or equal to A. So A is the smallest of the upper bounds. Least upper bound. The dual concept is greatest lower bound. So A would be a lower bound of S, and if B is a lower bound of S, then B is less than or equal to A. When least upper bounds and or greatest lower bounds exist, they have special names and special notations. The least upper bound for a set S is called the join of S and is denoted this way. For a finite number of elements in the set, sometimes we just write this. The greatest lower bound for S, again if it exists, is called the meet of S, and it's denoted this way or this way for a finite set. I guess you might be thinking, why do I have to deal with all these new terminologies when greatest lower bound and least upper bound are just fine and they're more intuitive than join and meet? And I would agree with that. But this is standard terminology and standard notation, so we are all stuck with it. The terms least upper bound and greatest lower bound tend to be used more often in analysis, where LUB and GLB are used as the symbols. But in algebra, the terms meet and join tend to be used more often along with these two symbols. One possible help in remembering this is in the Postset, in the power set, Postset, ordered by set inclusion, join is union, and this looks a lot like the union symbol. The least upper bound, as I showed you in an earlier example, of a family of subsets is simply their union. That's an upper bound, contains every member of the family, and it's the smallest one. And the least upper bound is the intersection, and this looks somewhat like an intersection symbol. So if that helps, good. But in any case, one just needs to learn these terms and notations. So let's take a look at two more Hasse diagrams for posets. And I'll see if I can get all this squeezed in here. That's not too bad right there, I think. This poset, if you look at this poset here and look at the set 2, 3, it has three upper bounds, 12, 24, and 36. 4 is not an upper bound for the set. It's an upper bound for 2, but not for 3. Among the upper bounds, there is the smallest one, 12. So that is the join. 2 join 3 equals 12. Over here, if you look at the same set 2, 3, it has two upper bounds, 30 and 42, but it has no least upper bound. Neither one of these is smaller than the other. Neither one of these divides the other. You should get used to the terminology smaller than, less than, or equal to. Again, doesn't have to mean the usual order. It can mean divisible by, or it can mean a restriction of, it can mean all sorts of things depending on the poset. Okay. Sometimes it's hard to break the, what you might call, habits of thinking of certain terms as meaning something. Mathematics is all about generalizing. We generalize the idea of an order relation, the ones you're familiar with, such as less than or equal to on the natural numbers. We generalize this concept, but sometimes we retain the terminology, and so you have to break away from the prejudice, you might say, of thinking of less than or equal to as always meaning what you're used to it meaning. 5 is less than or equal to 6. Under divisibility, 5 is not less than or equal to 6. So in this case, the set 2, 3 has no join. It has no least upper bound. Posets in which meets and joins always exist have special name. Before I give you that name, let's note that if a poset has the property that every pair of elements, every two elements, has a meet or a join, then every non-empty finite subset of P will have a meet or a join. So if every pair of elements has a meet, every 3 elements will have a meet, every 4 elements will have a meet, and so on. And I'm going to leave that for you to prove, because it's good practice. A poset is called a lattice if every pair of elements has both a meet and a join. And therefore, as I just got through saying, every non-empty finite subset will have a meet and a join. A poset is called a complete lattice if every family, finite, infinite, even empty, has a meet and a join. Okay. Lattices are arguably by far the most important types of partially ordered sets. If we go back to an earlier pair of Hasse diagrams, which I will attempt to find. Here we go. This is a lattice. Every pair of elements has a meet and a join. This is not a lattice. And it's not, this is a lattice, but it's not because it has a maximum element. That's not the reason it's a lattice. The reason is because every pair of elements has a meet and a join. Okay. As I mentioned earlier, if S is a set and we look at the power set under set inclusion, the join of any family of subsets of S, any family in the power set, is their union. It exists and is the union. And the meet is their intersection. So this postset is a complete lattice. This is the prototype of all complete lattices. For the natural numbers under divisibility, the join of two natural numbers is their least common multiple. The join has to be bigger than or equal to both m and n. In other words, has to be a multiple of both m and n, because that's what bigger than means when you're talking about divisibility. But it has to be the smallest integer that's a multiple of both of these, the least common multiple. The meet is the greatest common divisor. And that then generalizes to finite sets of natural numbers, non-empty finite sets. This is, however, not a complete lattice, and I'll let you think about why that is. Let's define a postset with this Hasse diagram. This is an infinite Hasse diagram. That's what the dots here are saying. The way this works is the underlying set is the set of natural numbers, 0, 1, 2, ... goes on forever, together with two additional elements, A and B. There are formal symbols, if you want, just anything but not natural numbers. And the way the diagram is drawn shows you that A and B are parallel. Both A and B are upper bounds for all the natural numbers in the postset, and the natural numbers themselves have the usual order. I'm not saying this is a terribly useful postset, but I constructed it for one purpose, and that is A and B are larger than all the elements of N, but are incomparable to each other. So the set AB, the subset of this postset, consisting of just A and B, is bounded below by every natural number. Every natural number is a lower bound for this set AB. So that set has infinitely many lower bounds, but it has no greatest lower bound, so it has no meet. Suppose that P is a postset, and the least upper bound of the empty set, the empty subset, now that is by definition the smallest of the upper bounds for the empty subset, the empty subfamily, if you want, the empty subset. What are the upper bounds for the empty subset? every element in P is an upper bound for the empty subset. Because every element of P is greater than all of the elements in the empty set. By default, there are no elements in the empty set. So every element of P is greater than all of the elements in the empty set. That's a little hard sometimes to swallow. Requires some thought. One way you can think of it is this. Suppose I said to you, every element of P is greater than all of the elements of the empty set. And you said, no, that's not true. Then I would say to you, fine, show me an element of the empty set that contradicts my statement, for which there is an element of P that's not greater than that element in the empty set. And you say, well, I can't do that because the empty set doesn't have any elements. And I say, aha, so my argument is correct. You could not contradict it. Well, in any case, what does this mean for the join of the empty set? It's the smallest of the upper bounds. Everything in the postset is an upper bound. So if the postset does not have a smallest member, the join does not exist. But if it does have a smallest member, that smallest member is the join of the empty subset. This too seems counterintuitive. When you think of join, you think of bigger. In the power set, under set inclusion, you think of the union. But for the empty subset, things get sort of topsy-turvy. And what I would suggest you do is think about the meat of the empty set. Use a similar reasoning to figure out what the meat of the empty set should be in a postset, in a lattice. Okay. All right. Here's another concept we're going to need in the text. Not too often, but we will need it. If you are sort of overloaded by this lecture, you could make a note of the timing in this lecture when we talk about order isomorphisms and come back to it when I do use the word order isomorphism. It's going to be some lectures hence, so this is not something you need right away. So the best thing would be to go through the rest of this lecture and then, if you need to, review it again later, which is fine. But you could skip this for now if you prefer. I always hate saying to students it's okay to skip something because sometimes that turns out not to be true and then I get in trouble. So take that as a warning, I guess. Okay, let's say we have two postsets. A function from P to Q is said to be order preserving, also called monotone or isotone, if whenever x is less than or equal to y, f of x is less than or equal to f of y. Notice here I used two different symbols for the less than or equal to. That wasn't necessary, but I did it hopefully for clarity. Oftentimes when you're reading a book, you'll see they use the same symbol even though it's two different posets. A function is called an order isomorphism between the posets if f is bijective and x less than or equal to y, if and only if f of x less than or equal to f of y. So order is preserved in both directions by an order isomorphism. Here's an example. Here are two postsets, Hasse diagrams. This postset is a power set postset. It's the power set of the set AB. So those are the subsets of that set AB. And we're under set inclusion. These are natural numbers under divisibility. Now, the function f from p to q, defined by f of the empty set is 1, f of the singleton set A is 3, f of the singleton set B is 5, and f of the set AB is 15, is an order isomorphism, and that's pretty easy to check. It's clearly a bijection. It's 1-to-1 and it's onto, and it preserves order in both directions. When there is an order isomorphism between two postsets, then the postsets have the same order structure. When the postsets are lattices, then they have the same lattice structure as well. In other words, the order isomorphism preserves meets and joins, not just for two elements, but for any subset of elements. And for this reason, order isomorphisms between lattices are called lattice isomorphisms. In essence, the only difference between two postsets that are order isomorphic is that the labeling of the elements is different. Their order structure is the same. Now we can explain one of the most important roles of partially ordered sets, and in particular complete lattices, in abstract algebra. In the study of algebraic structures, certain families of subsets play a particularly important role. For example, in the vector space Rn, Euclidean space, the family of all subspaces of Rn play a key role. And as you probably know from elementary linear algebra, the subspaces of R3 are the origin by itself, the lines through the origin, the planes through the origin, and R3 itself. These are special subsets of R3. They're closed under the vector space operations, addition and scalar multiplication. And more generally, all vector spaces, as well as other types of algebraic structures, such as groups, rings, and fields, have their associated families of substructures. So we have subspaces of a vector space, the subgroups of a group, the subrings of a ring, and the subfields of a field. If W represents any particular algebraic structure, vector space, group, ring, doesn't matter, then we'll denote the family of substructures by sub W. Of course, in this course, we're interested in the case of vector spaces, and so if V is a vector space, sub V is the family of all subspaces of V. In the second lecture series on group theory, we'll be interested in sub G, the family of all subgroups of a group. And in the third series, we'll be interested in subrings and subfields. There's another substructure for rings that is arguably more important than the subrings, and those are the ideals. The substructure family, sub W, is partially ordered by set inclusion. Substructures are subsets of W, and so they have set inclusion as their partial order. Also, this is particular to algebraic structures, really. Sub W has the property that the intersection of members of sub W also belongs to sub W. The intersection of any family of substructures is another substructure. You can see that with R3. If you intersect a line and a plane, for example, you'll either get the line, if the line was contained in the plane, or you'll get the origin. Okay. The intersection of two planes is a line. So that collection of substructures is closed under intersection. And it would look like this. If F is a family of substructures for W, then the intersection of F is also a substructure of W. There's a term for this, for closure under intersection. If X is a non-empty set, a family I of subsets of X is called an intersection structure if I is closed under intersection. The dual notion to intersection structure is a union structure, which is a collection of subsets of X that are closed under union. It happens that every intersection structure on a set X is a complete lattice. So the collection of subspaces of a vector space is a complete lattice. The collection of subgroups of a group is a complete lattice, and so on. Herein lies the importance of lattices in abstract algebra. How do we justify the statement that every intersection structure is a complete lattice? We have to find the meet and the join of subsets of I. We have to show that every subset of I has a meet and a join. If F is a subset of I, its meet is simply its intersection. After all, the intersection of F is the largest subset of any kind that is contained in the family members. But because I is an intersection structure, that intersection belongs to I, and therefore it is the largest member of I that is contained in the family members. In other words, it's the meet of the family. Let's look at the meet of the empty family in I. We know that's the intersection of the empty family. What is the intersection of the empty family? Well, by definition of intersection, it's the set of all elements of X that belong to every member of the empty family. But I say every member of X, every element of X, belongs to every member of the empty family, because the empty family has no members. That may be a little hard to believe at first, but look at it this way. Suppose you said, no, that doesn't make sense to me. I think that's false. That every member of X belongs to every member of the empty family. Well, then you have to produce an element of X that does not belong to some member of the empty family. You can't do that because the empty family has no members. So you cannot contradict the statement that every element of X belongs to every member of the empty family. That may take some thinking, but that is in fact accurate. It's logical. As a consequence, then, the meat of the empty family is in fact the entire set X. So we have a theorem that will be useful in a few minutes. If I is an intersection structure on X, then I contains X itself, which is therefore the maximum element of I. Every intersection structure on X contains X as one of its members. What about the join in an intersection structure? You might at first think that that ought to be the union. If we have our family F in I, you might think the join of F should be the union. But here's the problem. The union of the family F is the smallest set that contains every family member, but the union might not be in I. So then it can't be the join. Remember, I is our universe, this intersection structure. The only sets we have at our disposal are the sets in I. So if the union of F doesn't belong to I, then it essentially doesn't exist. So it can't be the join. Put more succinctly, an intersection structure doesn't have to be a union structure. As a matter of fact, none of the substructure families that we mentioned are union structures. And we can illustrate that by looking at the subspaces of R3. That's an intersection structure, as we've discussed. Here are the subspaces: the trivial subspace, lines through the origin, planes through the origin, and R3 itself. Intersections of any of these are, again, one of these. But if we take, say, for example, two distinct lines through the origin, their union does not belong on this list. It's not a subspace. However, we can still compute the join, we can still find the join by using intersections. By definition, the join of a subfamily F of our intersection structure I is the smallest upper bound for the members of F. It's the smallest member of I that contains all of the family members in F. And the key word there is smallest. How do we get the smallest upper bound for the family F? We take all the upper bounds for F and we take their intersection. Because I is an intersection structure, that intersection belongs to I. Now remember here that we are taking the upper bounds for f that belong to I. I is our universe. That's all there is. So you might say, well, what if there are no upper bounds to the family f in I, in our universe? Then we can't take the intersection. But the theorem we proved says that x belongs to I. So we are saved. Since x belongs to I, it's an upper bound for any family, f, contained in I. And so we have some things to take the intersection of. In symbols, then, the join of the family is the intersection of all the upper bounds for f, for the family f. And this is just another way to write it. And it's worth noting that an upper bound s, let's say s is an upper bound for f, if and only if s contains the union of the family. Again, the union of the family may not be in I, but it's a set. And so it's okay to say that an element of I could contain the union of f. So here's the complete picture. The meat of f is the intersection. The join of f is the intersection of the upper bounds of f. So the intersection, any intersection structure is a complete lattice. Meets are intersections. Joins are also intersections, but intersections of upper bounds. So for any of these substructure families that we've been discussing, the subspaces of a vector space, the subgroups of a group, and so on, they are complete lattices under set inclusion. So we're entitled to call them substructure lattices. In particular, our interest in this course is for each vector space to study the subspace lattice of the vector space. There is one problem with this definition of the join as being the intersection of the upper bounds of the family. And that is, it does not give us a picture of what the elements of the join actually look like. It's not constructive. It does show that the join exists, and therefore, because also the meat exists, we have a complete lattice. So this is very important, but it's not very satisfying from a constructive point of view. Now it turns out that we can describe the actual elements of the join, but that description depends on the type of algebraic structure. It's different for vector spaces than it is for groups or rings and so on. So we can't go into that matter now. But as we go into the text proper and discuss vector spaces at the appropriate time, I will show you exactly which elements of a vector space belong to the join of a family of subspaces. Final remark. I know that this is a bit abstract, and it will take some effort probably to absorb it. You may have to listen to the video a couple of times and think about this for a while. But I don't want to leave you with the impression that all of this is much ado about nothing, that intersection structures are esoteric objects. Intersection structures and union structures and their relatives occur throughout mathematics. And I want to give you some examples of that. It won't mean anything in particular at this point if you haven't studied these areas of mathematics, but at least it'll give you a sense that what I say is true. There's a branch of mathematics called topology. It's the study of structures that are known as topologies. And here's the definition of a topology. The field topology is a branch of mathematics that is designed to describe certain concepts: continuity, compactness, and connectedness. Those properties can be described, say, for the Euclidean plane, and would be done so in a class in mathematical analysis at about the same level as the course we're doing now in abstract algebra. But a topology class studies abstract topological spaces, and that's a generalization of what these properties would look like in R2. It's a wonderful subject. It's very interesting. I don't know whether it's taught these days at the undergraduate level or not. When I was an undergraduate, I took a class in what's referred to as point set topology, and it was a very interesting class. It's certainly taught at the graduate level, but whether it's still taught at the undergraduate level, I'm not sure, frankly. So, a topology on a set X is a family of subsets of X that is a union structure, closed under union, and a finite intersection structure, meaning that it's closed under finite intersections. Any set that has a topology defined on it is called a topological space. In the branches of mathematics known as measure theory and also probability theory, the following structure is fundamental. It's called a sigma algebra, and that is a family of subsets of a set X that contains X itself, the whole space, the whole set. It's a countable union structure, so it's closed under countable unions, and it's a complement structure, which means it's closed under set complements. And finally, here's an example from geometry where union and intersection structures occur. A subset X of R2, for example, is convex if whenever X and Y are in the subset, so is the entire line segment between X and Y. So a disk, a rectangle, a triangle, the solids, including the interiors, those are convex sets. This, for example, this shape is not a convex subset of R2, because if I take X here and Y here, the line segment between them is not completely contained in the set. theorem, the family of all convex subsets of R2 is an intersection structure, but not a union structure. So the intersection of any number of convex subsets of R2 is also convex. And you should think about why that is. It's not terribly difficult. But the union of convex sets is not necessarily convex, and you should be able to produce an example of that without any trouble as well. So union structures, intersection structures, even complement structures appear in various branches of mathematics. It's the intersection structure that's particularly important in abstract algebra, because the substructure families of vector spaces, groups, rings, fields are intersection structures.